Good afternoon, everyone. So today we have Dr. Cuong Nguyen, and Dr. Nguyen is an assistant professor in the Knight Foundation School of Computing and Information Science at FIU. Before joining FIU, he was an applied scientist at Amazon Web Services, working on machine learning with application to computer vision and natural language processing. Before joining Amazon, he was a postdoc at the Department of Industry System Engineering at the National University of Singapore. And then at the Department of Engineering at Cambridge University, he received his bachelor degree and PhD degrees in computer science from the School of Computing at National University of Singapore. His research interests include probabilistic machine learning and artificial intelligence. Okay, we can start.
Thank you very much for the introductions, and good afternoon, everyone. So today I will talk about the topic of building cost-effective machine learning systems. And this is a joint work with AWS, Facebook AI Research, and Vin AI Research. So let me first start with a recent special report from the IEEE spectrum that was recently published last month. It is called the Direct AI Reckoning. And the title is that deep learning has built a brave new world, but the cracks are now showing. So this special report is very interesting. It tried to analyze some of the current issues that deep learning and AI has faced. So the current revolutionary wave in AI has currently been empowered by deep learning, which is the technology behind the advancement of AI that you usually hear of today, if you are not familiar with the topics. So in that special report, one particular article that is very interesting is deep learning's diminishing returns, written by groups of scientists in MIT and some other industry labs like IBM, Watson, for example. And in this article, they argue that the cost of improvement for deep learning is becoming unsustainable. One particular interesting comparison in this article is comparing the cost of training a state-of-the-art image classification models. And the authors convert the cost of training those models into the equivalent carbon dioxide emissions. So as we can see in the plots here, right? So the upper plots show the percentage, the error rate of our state-of-the-art model on the very popular ImageNet dataset over time. And on the bottom, they show the equivalent cost of training those models when we convert them into carbon dioxide emissions. So for example, we are currently at around 2020, 2021, and the current state-of-the-art model for ImageNet is now around 10% of the error rate. And that converted to the carbon dioxide emissions, it is around the carbon dioxide emissions generated by an average US resident in a lifetime. And they extrapolate the data to predict that by 2025, we can reduce the error rate of our state-of-the-art model to around 5%. And the cost would be very huge. So the cost of training one single state-of-the-art model at that time would be around carbon dioxide emissions for the whole New York City in 1 month. And this cost even didn't consider the data cost, the cost for collecting the data and doing only annotations for the data. And so since we are talking about also the carbon dioxide emissions, I will borrow the terms in the environmental list terminologies to talk about some of the aspects of building the cost-effective deep learning systems. So I will call them the reduce, and recycles way to build a cost-effective deep learning system. So for example, reduce, we can try to reduce the training costs or the inference costs and also the data collection costs for the models. Reduce, we can reduce a model to use for several tasks or new data sets that we have. And recycle, we can also recycle a part of a model for our new data or new tasks. So, for example, one way to reduce the cost is to use active learning. What is active learning? So if you are familiar with the usual way that people train machine learning systems, that is usually called the passive learning process. So in the passive learning process, we have a set of unlabeled data. And for example, in ImageNet or an image understanding task, we collect a lot of images of objects. And then we pass the whole set of images to an annotator who are a human. And the annotator will label those data. For example, label those images and put them into different categories, cats, dogs, trees, for example. And then we collect all those labeled data set and we train a machine learning model using a machine learning algorithms. So that is the usual way that we do machine learning. This is called passive learning. We can do it in an active way, in which, let's say, we also have a source of unlabeled data like before, but we do not give everything to the human annotator. So we will use a query strategy to select a data, an unlabeled data, for example, the image that we think would be most useful for our model. And then we give it to the human annotator. The human will label the data, and then we add the new data to our current label data set. And then we will use the new label data to train or update our model. And then we repeat this process until we achieve a desired accuracy for our model. So, by this active learning process, we allow the machines to choose what it learns. And the aims of active learning is to learn a good models with a very small number of label samples. And this can help us to reduce the data annotation cost as well as the training cost for our model, because now our data set is smaller and we would require less computational time to train our model. So this is the first aspect of building a cost-effective machine learning systems, that is to reduce the data collection costs and the training costs. So the second aspect that we can do is to reuse the model. So we can use continual learning to reuse our models. So So what is continual learning? So continual learning is formally defined as Raju, you have questions?
Yes, please. I'm curious about accuracy. If you reduce the amount of data that you use to train a model, doesn't that affect the accuracy of the model as well? So doesn't active learning make things worse from an accuracy standpoint?
No. So the goal of active learning is to maintain the same accuracy with less data. So we will, so using active learning, we can select the most important data points to train the models. And that's why it would help us to reduce the number of data points without the loss in accuracy.
But okay, sorry, I'm new to the area, so that's why the question: who decides what data is important?
We will select the data points. So the models, right? We will select the data based on the need of the models, based on where the model is most uncertain. So let's say you can, if you collect the data randomly, you can collect data points that are close to each other. And those data points are not very informative compared to just one single data points in that area. Right. So that's why, let's say you want to spread the data points on your evenly on your input space, for example, instead of, let's say, collecting many data points that are clustered together. That would not be very helpful for your data, and it increased the number of data points that you require.
So just to wrap up, I know it seems like you need either some automated technique to choose the right kind of data, right, or a human intervention. So I'm guessing it's automated somehow.
It's automatic based on the current model.
Right. And although you're doing many repeated rounds of training with active learning, because the size of the data is small, the overall cost is small relative to just doing it once with non-active learning.
So yes, you would do several rounds of training your models with the new data, but you can actually update it rather than retrain the model from scratch every time, because you already have the old model trained on your old data, and now you have additional new data, so you can just do an update. Ananda?
Yeah, Cuong, so how this is different from a feature selection approach? Is active learning?
Feature selection is different in the sense that you will select the features on your data, but active learnings would not touch the feature set. It only selects the data itself.
I see.
Yeah.
Yeah.
Yes, Chris?
Yeah, sorry if we don't want to delay you too much. Just to follow up to all these questions here. So by what you achieve is you're going to have to look at less data to achieve the modeling, but it sounds like it will not have an impact on the model size ultimately, right? It's still going to be the same model, just trained with differently selected data.
Yes. So you would use the same model for both of them.
Okay.
Yeah. Roger?
Yes, Professor, I have a question. I can see that working very well for tabular data if we can increase the distribution, right? That way we can capture a bigger overall picture. But do you have any idea how that would work for computer vision when we have images?
You mean active learning?
Yes, correct. Active learning.
Yeah, so for computer visions, active learning can work pretty well. So there are recent research that apply active learning to some of the medical image domain. So, and it works well in these cases. People actually rarely use it for natural image domain because we already have a very large data set like ImageNet for the natural image. So there's no need for active learning there actually. But we usually apply active learning to new domains or new tasks. And it works pretty well for like X-ray image or medical images.
Okay, thank you.
Yeah. So, okay, then let's me move on to the second part. So we are discussing about continual learning. So continual learning is a more general form of online learning. So online learning is that the data continuously arrive and your model have to adapt to the data, to the new data. But online learning sometimes assume the data may be IID and you have a single task for your data. But continual learning is that you may have new tasks that your model have to solve, and your data for the task that you receive may be non-IID, and your task may changes over time as well. So for example, you do image classifications, you may have new requirements for your task, you may have new classes. For example, you may observe image of dogs, cat, and then later on you observe image of mouses or horses, for example. Then you have to adapt your models to those new requirements. And also another requirement is that your models have to be used for several different tasks at once. And in continual learning, the goal is to adapt your model to the new data or the new requirement without looking at the old data. So there are these restrictions. And usually when you do continual learning, you have to reuse the model for a stream of tasks. So you can think of like robots where they continuously explore the environments and have to adapt to a different form of data and different tasks when they discover more information about the environment. And so this is a example of a very popular benchmark for continual learning in the literature, which is called the split MNIST. This is a very simple benchmark. So it used the MNIST dataset. So the MNIST dataset contains of images of digits from 0 to 9. And you have to train basically classifier for these images to classify between different digits. And the split MNIST benchmark would start with giving you images of 0 and 1. And then you train your neural networks model to classify between 0 and 1. And then in the next task, they give you image of 2 and 3. And then you have to adapt your models to classify both 0 and 1 and also 2 and 3. And then at the next iterations, they give you 4 and 5, images of 4 and 5, and then you have to adapt your model to predict images of 4 and 5. And also you have to do well on previous tasks like 2 and 3, 0 and 1. Okay, I have a question from Luz.
Yeah, it was a very simple question. When you say you adapt a model, since you're referencing to our neural network, do you mean adapt the architecture?
Usually, it would mean that adapt the weight of the neural networks.
Okay, thank you.
Or you can slightly, you can slightly change the architecture a little bit, but would not be usually the requirement for continual learning is that you don't change the architecture significantly. You can extend it a little bit.
Wonderful, thank you.
Yeah. And so, so this is the second aspect of building the cost-effective machine learning systems. And now I'll talk about the third aspect, which is also the focus of my talk today, which is recycle the model using transfer learning. So first, let me introduce the definition of transfer learning. So in transfer learning, the aims is we need to develop methods to transfer the knowledge learned from one task to another task. So the task that we have the knowledge that I already learned is called the source task, and the task that we want to solve is the target task. And the goal of transfer learning is that the hope is that if we use the previously learned knowledge, we can potentially reduce the data required on the target task and subsequently the computational cost when we train on the target task. So here are two comparisons for a traditional machine learning process and a transfer learning process. So on the left, for a traditional machine learning, we will have different tasks that we need to solve. And for each task, we need to collect a different data set. And then we train a model individually for each task. When we do transfer learning, we will have the source task that we will learn. We have the data for the source task. We learn our models. And then we use the knowledge or the models that we have from the source task, and we transfer it to a new task together with a data set for the target task. And our data for the target task would be smaller than if we train it from scratch. And I think I have, okay, so in the context of deep learning, what does transfer learning do? So in transfer learning, for deep learning, the source task, we will train a deep learning models for our source task. So this is the different layers in the deep learning models for the source task. And we have the target task that we want to transfer the knowledge to the target task. So what people did in transfer learning in this case, that we would take the first part of our models and we use the first part of our models for our target task, including on the weight that we already learned. And then we will replace the upper part of the model, which we usually call the head models. We replace it with the new one, and then we would train the new model for the target task. So basically, that is, we recycle the first part of the models for our new task. So on the orange part of the models here, a copy from the previous models that we already learned. And the purple part of the models is the new part that we need to learn from our target data set. And there are two simple methods to train these target models. So the first method is called retraining, in which we will freeze all the model parameters in the orange part here using the previous settings and the previous value from the source task. And then we only train the purple part, which is the head models. The second method is called fine tuning, which we would initialize the orange part by the weight we obtained from the previous models. But then when we train, we will modify the weight for all the whole target models by running a few stochastic gradient descent algorithms, iterations, for example. So both of them work well in practice, although for most cases, fine-tuning would usually give you a better accuracy than retraining only the head. But of course, fine-tuning is more expensive than doing the retraining only. So in this context, there are two research questions that I'm currently interested on. So first is the source task selection problem. So let's say we have several source tasks and we have a target task. Which source task should we use to transfer to the target task? And the second research question is the reverse direction. It is called the target task selection. So let's say we, in this case, we assume we already have the source task and we have several target tasks that we need to solve. Then which target task should we prioritize if we know that we would be transferring from the source task? So which target task should be the most promising and the best to solve? So here, when I mention a task, it is usually either be represented by a data set or a pre-trained model for the task. So to deal with these two research questions, we look at a more general formulations or more general problems that can help us approach the two previous questions. So this problem is called the transferability estimation problems. So what is transferability estimation? This problem tries to estimate how easy it is to transfer the knowledge from one machine learning task to another. So let's say here we are given two data sets and we want to know in a very cheap way or very quickly whether if we do transfer learning, how effective the transfer learning method can be. So basically, we need to develop a measure or a numerical score that would tell us how effectively we can transfer from the source task to a target task. And ideally, the transferability measure that we develop should be easy and very cheap to compute. And we want to do it without any training or with very minimal training. So if we can look at an examples on phase dataset, for example. So let's say we have 4 different classification tasks, which is identify whether an image is an image of a male or female, whether the image is a bold or not bold person, whether the person is smiling or not, or whether the person is wearing a lipstick or not, for example. So we want to know whether it is easier to transfer, let's say, from male to bold, or it is easier to transfer from male to smiling, for example, or from male to lipstick. So if we think of it intuitively, male and smiling would be relatively more independent compared to, let's say, male and bold, because if we know a person is male, then likely he may be more likely to be bold than a female, for example. And also male transferring to lipstick would be easier to male transferring from smiling, for example. So this is the intuitions for doing the transferability estimations. And so there are a few reasons why we want to do transferability estimation. So the first reason is that it would help us to understand the relationships or the structures between the tasks. And if we can know the relationships or the transferability between the tasks, we can select groups of highly transferable tasks to train jointly. And to train different tasks that are highly transferable with each other, we can also reduce the number of data required for each task. And we can also, like I said before, we can select a good source task to do transfer learning. And it would help us to reduce the training data size and also the training time on the target data. And we can, finally, we can prioritize the target task for transfer learning. So how do we approach the problem? So let's consider a very simple case. Let's say if the source and the target task share the same input. For example, in this case, we have the same input image, and the source task could be whether this image is a male or female. So, so this is an image of a male, and the target task is whether the person is born or not. So we would have the set of input, and each input would have two labels, one for the source task and one for the target task. So this is, we can write down it. So let's say the input images could be x1, x2, xn, the same for the source data and the target data. And the label for the source data would be Z1, Z2 until Zn. And the target data label would be Y1, Y2, Yn, etc. So one easy way to do to estimate the transferability is just to look at the conditional entropy between the two label set. So for example, we collect all the source label into a set of Z1, Z2 into Zn, and then we collect all the target label into a set Y1, Y2 into Yn. And then we compute the empirical conditional entropy of the target label given the source label. So this is the formula for the conditional entropy, in which from the data, we compute the empirical Jones distributions of the different labels for the target set Y and the source set Z. And then we also compute the empirical marginal distributions on the source label. And then we use the usual conditional entropy formula to compute the conditional entropy between these two random variables. So we have some properties of the conditional entropy. So this is very easy to compute, and it just be based on the statistics of the training labels. So it would be very fast and easy to implement. If you implement it in Python, it will only require like 10 lines of code. And we can actually show that in theory, the conditional entropy is related to the data log livelihood. So we can show that the log livelihood of the transfer model would be low bounded by the log livelihood of the source model minus the conditional entropy. And how does the conditional entropy works compared to the actual transferability? So we measure the transferability or the intransferability as the actual error rate when we do the actual transfer to our test set. And we compare the actual error rate with the conditional entropy, which would be the proxy for the error. And if the two quantity is highly correlated, then it shows that the conditional entropy can actually be used to predict the intransferability in this case. So for example, this is the two typical results that we have. So we transfer from the male classifier to 40 different attributes on the face dataset. And we can see that the conditional entropy is highly correlated with the actual error of the classifier when we transfer to the target data. So it shows that the conditional entropy is a very good intransferability estimation. And it's also the same for other attribute as well. So if we transfer from wearing lipstick, we will receive a very similar results. So so here, just a reminder that conditional entropies measure the uncertainty in the data. So it is actually measure the intransferability instead of the transferability. So if we want to convert it into transferability, we have to take the negative of the conditional entropy. So this is for the simple case. So how about the more general case where the inputs are different on the source task and the target task? So in this more complex settings, we can also actually apply the conditional entropy. For example, we can take the source dataset and we train a model on it. Then we can use the trained model to predict a dummy label on the target data. And then we can compute the conditional entropy between the target and the dummy labels. It can give us a reasonable transferability estimations, but we actually have a better to do it, which is called the leaf method. So for this method, we also train a model on the source task. And then we also use the model to predict the dummy label on the target task. But we don't predict a single dummy label. We predict the distributions for all the labels. And then we also compute the empirical conditional distribution on the data set, on the target label set. But now we compute it with the label distribution instead of one single label. And then from this, we can compute it using a classifier that we call the expected empirical predictor. So what does this classifier do? So it will predict a label for our target by running from two steps. So the first one is that it will draw a dummy label from our label distributions. And then the second step is that it will draw the target label from our conditional label distribution, from the empirical conditional distribution. And then the leaf estimator is defined as the average log likelihood of the EEP, which we have the formula for it here. So this formula is actually very easy to compute. So usually if we already have the model theta pre-trained on our source data, we only need to run one forward pass through the whole target dataset to obtain the probability distribution for each of the label data points. And then we compute the conditional probability distributions and then sum up on the likelihood here, on the log likelihood here. So this is an illustration for how LEAP works. For example, we want to transfer a classifier from land animal to sea animal. So assume we already have a classifier that can help us to classify land animals. And we have a target data set that contains the sea animals. So the first step is that we already have a pre-trained models on the land animal. So we just apply the pre-trained model on our sea animal data. So the models would give us some dummy label distribution. So for example, this image here, the models, because this is a land animal classifier, it can predict that, okay, this is a dog with probability 0.8, maybe a horse with probability 0.15, and then a giraffe with probability 5%, for example. And we give the classifier this image of a seahorse. It may, it predict that this is a dog with 10% confidence. It may be a horse with 0.4 probability, and maybe a giraffe 0.5 probability. So those are the dummy labels that we obtain from our source model. And then from those dummy label, we can compute the conditional probability distributions for each of the target model, for each of the target label given the dummy source label. And then we use the previous formula to compute the leap measure. And so here are some properties of leap. So it has a very clear interpretation, which is the average log likelihood of the EEP. So some previous method to do transferability estimation doesn't have a very clear interpretation. And our method leap is actually have a very clear interpretation. And it is also very easy to compute. As I said before, you only need to run the models through the target data set once, one forward pass, and you do not need to do any back propagation. And you also don't need to train the model on the source task, because usually we have on the available pre-trained model for all the popular benchmarks. So you can just reuse them. And it can be applied to almost all modern deep networks. We can also show theoretically that the leap method is related to the log likelihood of the target data and also the conditional entropy. So here is also some empirical evaluations of leap, similar experiments like what I showed before. We try to see the correlations between leap score and the test accuracy when we actually do the transfer. And we can see that for a different source data, for example, transferring from ImageNet to CIFAR 100 and transferring from CIFAR 10 to CIFAR 100, the leap score can actually be very highly correlated with the test accuracy for both transfer learning methods, fine-tuning and retraining the hand. And we can also use leap for source model selections. For example, in this experiment, we select 9 different models to transfer to the CIFAR 100 data, and we compare leap with 3 other state-of-the-art method, which is the negative conditional entropy that I discussed before, the H-score, and also the ImageNet top 1 accuracy. And as we can see here, the leap score corresponds very well with the test accuracy for the source model. ImageNet accuracy doesn't work very well, and this is very uncertain. The NCE score and H score kind of works, but it doesn't work as well as the leap score. So just a summary for my talk. So I have described in this talk some aspects of how we can reduce the cost when building a deep learning model. And I have presented here how we can do transferability estimations and how we can apply it to transfer learning. And also transferability estimations can also be applied to other settings like continual learning and also multitask learning as well. So this is my collaborators for this work. And thank you very much.
Okay, thank you. So before I end the meeting, I wanted to mention Dr. Wang joined our school in August and is now recruiting students for his research group. So if you are a student looking for a faculty advisor, please feel free to contact Dr. Wang. And also, Dr. Wang, thanks a lot for your wonderful talk, and also thank everyone for attending the seminar. And see you next Friday.